Yes, hello. This is the lecture number 4, part 1, devoted to the weak star topology. So before we start, let me, let's say, recall and a little of, let's say, introduce some of the notations that we'll be using today. So maybe let's start with the usual. So let's say let E be a Banach space. Then, of course, we should remember we have the so-called duality map that goes from E to the E double star, double dual. This is defined in such a way that, of course, in such a case, J of x is a linear function on E star. So we have here the J of x applied on F by the definition. This was equal to F of x. Then we of course know that the J of x has the norm, put here like a bullet, is equal to x. So this means simply that this is an isometric linear operator, isometric linear operator. Then of course we can identify, we have natural identification of E with its image, and this one is of course sitting inside the E double star, possibly not equal, but in the case J of E is equal to E double star, we say that E is reflexive. We also introduce the notation, maybe put it like this: B, I will denote this unit closed ball in E. So this is in E such that x is smaller or equal than 1. 1 looks like 1. And then we can also introduce B dot star. This will be F belonging to E star such that F is smaller than 1. And then we have also B double star, which is equal, and here I will be using psi belongs to the E double star again. This will be psi smaller equal to 1. So as you notice, I will try to keep notation clean. That means x belongs to E, f belongs to E star, that's a functional, and this one is the psi belong here. If we deal with the case of the third, then I will write psi belongs to the E, and we will put here 111. Okay, so this how we will be applying this notation today. So let me start with the main theorem for today. This main theorem is called the theorem, Kakutani theorem. And this is called the Kakutani theorem. So we have the following formulation. So let's say let E be a Banach space. Then we have the following statement. So E is reflexive if and only if the ball, unit closed ball, is compact in the weak topology, in sigma. That's how we denote this weak topology in order to make sure that we don't mix it up with another topology. So this is Those are the functionals that induce the topology. Those are the functionals that induce this topology on E. So this is topology on E. Okay, so let's prove it that it is compact. So so let's prove the first implication. Means we go that way. So proof, and we go this way. So assume that maybe I'm too squeezing. Sorry. Proof. Assume that E is reflexive. E is reflexive. Very good. And since B double star is, this is compact, is compact in sigma, and we put it really. So this is the topology on that one. So this is weak star topology. So this is weak star, weak, call it star topology, topology on E double star. And this is by Logu theorem. It will be sufficient, to conclude that B is weakly compact by checking that the map J minus 1 that goes from E double star to E, that's invertible, this is minus 1, is continuous. Is continuous with respect to, okay, we have two topology. So let me maybe write it down like this. So we have here two topologies. So first, continuous with, here we have this topology, star topology, and here we have here this topology. So this is E and this is E star. So this must be continuous with respect to this topology. So that one is here and this one is here. Once we know it is continuous, then in such a case, the conclusion follows from the fact that continuous image of a compact set is compact, that the image J minus 1 of B doesn't show, it's still ugly, twice is equal to B is compact, is weakly compact from continuity of J minus 1. So that's what we have. So it is enough just to check that this map, so checking, so let's say verification. So verification, we need to show, so what do we have? We have here this is the map, so that it starts here, and this is J minus 1, it goes here to E, and I need to consider it, of course, let's put it clearly, so this will be with this topology, E, and this is E star, and here I'm taking with this topology, E, and this is E star, and I need to show that this map is continuous. So how it is done? So using the fact that this topology is defined by the, so the topology on E is defined by the maps F, where F belongs to the E, to E star, yes, to the E star. So this maps here. So that means the map J minus 1 is continuous with respect to this topologies, if and only if that composition, this composition of J minus 1 composed with F continues from that set to R, from the E double star R with respect to this topology. So that's quite simple to check. So let us check it. Namely, okay, so let's write it down. Suppose suppose here that x, J of x is equal to the psi, and then, of course, that means that J minus 1 of psi is equal to x, and then you have here that in such a case, what do I need to show? That F composed with J minus 1 applied on psi, so this will be the same as F applied on x. But that one, what is this one? This one is, that one is, yeah, that's nothing else then. J of x, let's say like this, this is, sorry. Okay, so this is F, and this one is equal to, yeah, maybe we should go slower. Yeah, so let's write it down. This will be J minus 1 of psi, and that one I'm getting here, this is the same as F on x, n of x. And clearly, let's write it down. What is x? What is f of x? F of x, this is the same as J of x applied on F. Oh, that's what was the definition. Just remember, that was the definition of our, yes. 1 second. That was the definition here. You see, this is the, not wrong color, it's supposed to be red. No. This is this definition here. So if you write it down here, that's exactly, this is the exact version. So now I can write it down. This is psi on F. And I look, what do I get here? Wow, I'm getting here that this is the functional, and let me denote this functional like a psi of F applied on psi. So what is this functional? This is the functional psi on F belonging to E star, maybe, no, yes, E star, triple star, such that psi of F on psi is equal to F, psi on F. epsilon f. So that's exactly the functional that generates the topology on E double star. This is exactly the functional that generates the topology on E double star. So that's it. This is equal. Put it here. This is minus 1 psi of f, and psi of f belongs to E star, because this is exactly our f. Like that. Yeah, finished. It's continuous. So now, since this is continuous, let's say the continuous image of compact set is compact, and we are done. In order to prove the second part of the Kakutani's lemma, it's not so trivial. We need two lemmas. And we start with the first one. So, namely, let's formulate the lemma and let's write it down. Lemma number one, we associate with the name Heli. And let's formulate. Let E be a Banach space. And suppose you have here the set of functionals, finite set, f1 and fn belonging, so not belong, contained in E star, and suppose gamma is a vector from Rn. So there is n, this is the n. Then we have the following. The following two conditions are equivalent. Following two conditions are equivalent. So put here, first condition is basically the following. For every epsilon larger than 0, there exists an x belonging to the unit ball in that one, such that here maybe we should indicate that this choice of this point belongs on the epsilon. So then we have here that f, and this is x, and I put it again little epsilon to remember that one is always, and this will be k, for every k equals 1 to n. Not good. Squeezing. Let me try to erase it. I want to erase it. And then let me do the erasing. Can I erase it? Bigger. Better. Oh, everything erased, even the grid. Very good eraser. So this one. And now I have to change to the small dot. Where is my small dot here? And then we have for every k is equal 1 to n. We have here that, put it like this, fk of x, and this will be again that epsilon, and let's come on, change, doesn't want to change. Okay, change, close, and this will be minus, and this will be gamma k, smaller than epsilon. The condition 1 is here. So the condition 2 is the following. So actually, this is for every beta is a vector, b1, bn belonging to Rn, we have the following inequality, namely I take this beta and I put here k is equal 1 to n. This is beta k and I put here gamma k. Smaller equal and then take the norm of the linear combination k equal 1 to n with the coefficient beta k of the fk. These two conditions. So let's do the proof quickly and let's reveal what actually is going on with the condition R. So notice, it's okay, consider, maybe start like this, consider the linear map, T that goes from E to Rn, and it is defined like this: T of x is just simply equal f1 of x, f2 of x, and this will be fn of x. 10. The condition A simply means that gamma belongs to the closure of the image of the unit ball under this transformation. Here, of course, here we consider this space Rn with the norm infinity, means supremum norm, maximum norm, depends how you call it. So this condition means, indeed, we simply have here that, write it down, gamma belongs to the T of B will be equivalent to say that for every epsilon larger than 0, the ball, but this is the ball in the space epsilon ball in 0, of gamma, and that one maybe nicely, gamma, and this is of course in Rn with this norm here, intersection TB is non-empty. And that of course implies that this is the same as for every epsilon larger than 0, there exists an x belonging to B such that T of x belongs to B epsilon gamma. And then write it down again. So this is the same again as for every epsilon larger than 0, there exists an x belonging to B such that, and now we can write this. So okay, that means simply that distance with the maximum, so put it like this, k is equal 1 to n, and now we take tx, so what is the component of this tx? So f1, a kth component, take k component. So I'm getting here that this means fk on x minus, and the k component of gamma is gamma k, smaller than epsilon. So that's the condition A. So in such a case, we already know what it is. So let's prove that the condition A implies condition B. Proved. So put it like this. A implies B. So what do I have here? Let's say like this. Notice that the following thing. So let's say like this. Okay, let me write it down. I need to consider, so look here, what do I have here? I have here the condition B. Okay, so I write it down like this. Consider the following inequality, the following expressions. So I write it down like that. I take the absolute value, take n is equal 1, k is equal 1 to n, and then I have here beta k, and then I put here fkx, and I have here this x with this epsilon. So this was chosen, so A is true, so I have that one. So minus, and I put here again sigma, and this will be beta k, gamma k, k is equal 1 to n, and this will be gamma. Take it like that. So now I put everything smaller, so this is still equal, so this will be equal, and I have here k is equal 1 to n, this will be beta k, and now I put here up like that, and then I have here fkx. This is this from the condition A, so x epsilon, minus, and this will be a gamma k, close it. Now use the let's say, in the absolute values, k is equal 1 to n, absolute value of beta k, and then here I have absolute value of fk x epsilon minus gamma k right now, and that one is of course smaller strictly, so that one is smaller by the condition A. This is by condition A smaller than epsilon, so I'm getting this is smaller than epsilon, but since beta can be, we didn't assume possibly 0, so we have to add that one, put it again, this one, and then in such a case I'm getting here that, and I put here sigma k is equal to 1 to n, and this is beta k, and we will call this sum, just a sum, so s, k is equal 1 to n, we call it s, so this will be equal epsilon times s, epsilon. So we have here that for every, so we got that for every epsilon larger than 0, there we have here there exists an xi prime belonging to B such that this expression here, put it here, this expression, and I put k is equal to 1 to n beta k, and that one is f k x epsilon, and this is minus that guy k is equal to 1 to n, and this is beta k gamma k, is smaller than epsilon times s. Good. Yeah, good. So now what do I do here? I just simply say I have this expression, so I can rewrite this expression, just simply use the triangle inequality to get that one on the left. So I put here sigma k is equal to 1 to n beta k gamma k, and I say smaller equal, and this is epsilon, I keep it, epsilon times s, and this will be plus, and I put here that guy here, this is k is equal to 1 to n beta k f k x epsilon k. So I look at that one and say, oh, I can actually rearrange it a little. So I put here like x, and I put here like this, absolute value. So now I have here, I put here everything, big sum inside. So this is k is equal to 1 to n, and this is beta k f k, and I put here x, close it, and I see, x is x epsilon has the norm smaller equal than 1, so I can rewrite it down. Smaller equal epsilon s plus, and I replace it by the norm of that guy. K is equal 1 to n, beta k f k, and we got it. And that's true for every epsilon. And look, there is nothing here. In the beginning, there are no x's, and here there are no x's. So this inequality here can be done, let's say, can be simplified, because that's for every epsilon. So by passing with epsilon to 0, we have that this k is equal 1 to n, and k is equal to 1 to n, and this one is beta k gamma k. Gamma k actually is smaller equal, and that one is equal to norm of sigma k equal to n and beta k f k. And since beta was arbitrary, for any arbitrary beta equals beta 1 beta n, that implies this is the condition B. So we proved that A implies B, and A implies B, and that's exactly, now let's go, B implies of A, and that's exactly the condition B that we have satisfied. We have it. This is for every, so this is for every beta, and then let's say like this, we need to show that this condition, so we need to show that the B implies that gamma belongs to the closure of B under this mapping T. Okay, that's exactly what is supposed to be. So assume for contradiction that gamma does not belong to the closure of B. And since this is the image of a ball is a convex set, so this is definitely a convex set. Gamma is a single point by strict separation theorem. So what is the strict separation theorem? This is Banach geometric version 2. We have here, there exists a functional. So we can say functional belonging to Rn, but we can identify this functional, we can identify it with a functional with a kind of a, put it like this, star. So we can identify this functional, so we identify with a vector beta belonging to Rn. So that means the functional on the vector, not x, x is in the other space, T, where T is equal T1, T2, Tn. So this functional will be just simply beta k tk. You understand? Okay, so maybe sorry. So I would write it down. So put it like this. So if you take T is a T1, Tn, so this belongs to Rn. So this functional applied on this vector T can be written as the sigma. That's the representation. K is equal 1 to n beta k tk. So that's the representation. So if we have that this is separate, so there exists an alpha belonging to R, then we have here a strict separation. So that means for every x belonging to B, I have here the separation. So what it separates? So we have here, remember how the image was defined. The image was defined here. This is the map. This is the map. Here. Oh, that's the map. Yeah. Oh, here. That's the map. So that means those symbols is in the means. Okay. So if I have applied now, I'm getting here that we have here sigma k is equal 1 to n. This is beta k, and then we write it down fk applied to x smaller than alpha, and that one is smaller, and we are getting here k is equal 1 to n, and this is beta k gamma k. Very good. And that's true for everything. So that's true for everyone. So maybe let me maybe let me rewrite it so I can put it again. Write it in the different form, B, and now I put it like that. That one I put here, and this one sum goes inside to n, and this is beta k f k x. Close it, smaller than alpha, smaller than k is equal 1 to n beta k gamma k. And now I can take the supremum. I can apply it here, supremum. Supremum x belongs to b on the left hand side. That's the upper bound, so I have this supremum, and of course that gives me that I'm getting here the inequality. So that becomes simply the norm of this k is equal 1 to n beta k f k, and then norm, and this one is smaller equal than alpha, smaller than k is equal to 1 to n beta k gamma k, and that implies that this is basically the contradiction and with the b, and which contradicts b. So that means we proved the lemma 1, we have it. So let's pass to the next lemma. The next lemma is also a lemma. Okay, let me go to the next answer. I go here. Yes, so put it lemma number 2. Lemma number 2. And this is Goldstein. Let me write it down correctly. Name Goldstein. And let's formulate the lemma. Let E be a Banach space Ten JE, sorry, not JB, still not nice. JB is a dense in sigma, and this is E double star E star topology, subset of the ball with the double star. So this is the ball in the space, second dual. Therefore, by the fact that you can always, let's say, therefore, because this is a topological vector space topology, so you can scale the ball. You can take the ball of the radius 1, and you can take the ball of any radius, and they have the same properties. So that means the whole space can be covered with such balls. So in such a case, therefore, we are getting here that J of E is dense, again dense, with respect to sigma E double star E star topology in E double star. So that's the statement. Let's go and do the proof. And the proof goes like this. So take any, and I put here, psi naught belonging to E, to the B double star. So that means this is the B double star. That means the norm of this double star is smaller equal than 1. Just to remember it. So I take that one. So what do I need to show? I need to show that then for every basic neighborhood of psi naught, and let me remember, with respect to sigma, to this topology, and put it like this, V, So what is V? That means, of this one we have that the V intersection J of B is non-empty. That means we need to show that that there exists an element that belongs. So we need to show that there exists an X belonging to B such that J of X belongs to V. That's what we need to show. So what is the basic neighborhood? So basic neighborhood of psi naught. So what is this? So of course this means, let me say like that, we need epsilon larger than 0, and then I need a final set. This will be like F1, F2, we have here Fk, k of them, Fk. And what do I have here? I have here that we have here that this V can be written as a V. This is capital F, those are the functionals, this is your epsilon, and that by the definition this is set of all psi belonging to the E double star, such that for each of those, so this means such that for every k is equal 1 to n, I have absolute value psi minus psi naught, Fk, smaller than epsilon. So we need to find, we need to find X belonging to V we need to find X belonging to B such that J of X belongs to V. J of X belongs to V. And what does it mean? That means simply we need to find an X belonging to B satisfying the conditions that for every k is equal 1 to the n, that one is satisfied. So psi is now becoming your Jx. This is becoming your Jx. So let me put it like this. This one is equal, and put it here, J of X minus psi naught, and this is Fk smaller than epsilon, but you can rewrite it. So this is again, for every k is equal 1 to n. What do I have? I have here that this means simply separated, means this will be Fk of X minus, and this will be psi naught Fk smaller than epsilon. So let's call that guy. Let's call this one. This one is equal to F, so gamma k. This will be my gamma k. So that's what I need to prove. But then I say, okay, this condition is actually equivalent by the lemma number 1 to that one. So what is my condition? That for every beta belonging to Rn, I have that my in n is equal 1 to n, sorry, k is equal 1 to n, and this one is equal beta k gamma k, smaller equal, and here I have here that in is simply k is equal to 1 to the n, and this will be beta k Fk. Do we have this condition? So let me notice, however, put it like this, however, so this call this star. Notice that I can rewrite this star like this. This star k is equal 1 to n, this is beta k, and replace it. This will be like a, what is Fk? So this is psi naught on Fk close it. So this is the same as k is equal 1 to n, and here I have here, sorry, big one, and I put here this guys here, k is equal 1 to n, and then this will be this will be psi naught, and this will be that way, k is equal 1 to n, and this is beta k f k, yeah, and here psi naught has the norm smaller equal than 1, so use the norm, so smaller equal, this will be the norm of psi naught times the norm of k is equal 1 to n, and this is beta k f k, but psi is smaller equal, so that means we are getting smaller equal k is equal to 1 to n beta k f k, and we proved it. So we proved it. That means we get the statement proved of the Goldstein lemma. So the proof is finished. So now, of course, I need to make a short remark. Also, you know that J of B is always dense in the topology, dense in B double star, in the topology sigma, and this one is sigma star, sigma, like that. But in the case of strong topology, it will be dense if and only if it is dense if and in B double star, if and only if the space is reflexive. That means that one. This is dense in strong topology, So that means strong topology, of course, because JB is closed subspace. JB is closed subspace. Maybe not the whole space, but it is definitely the. So now we can finish the proof, so underline and finish the proof of the Kakutani's theorem. So Kakutani theorem. Proof, and the remaining is this one. Implication. So we will need to show that actually the let's say like this that the space is reflexive. So if B is weakly compact, that means with respect to this topology, then the space is reflexive. Maybe like this 10. Maybe I should be more specific. Okay, this topology 10. We need to show that the space E is reflexive. The space E is reflexive. So how we are going to do it? So again, here it comes again the similar picture. Here is the space here. Here we have the compact set B. And here we have the duality map J. And duality map goes where? It goes to the E star star. That's the duality map. And very good. And then here we have the other ball sitting here, the other ball. And except I have to have it with the appropriate topology. So I need to take here the topology E star, and here I need to take this topology E double star, and this will be E star. And I need to show this one is continuous. And I put here question mark. Is it continuous? So let me verify it. So let me do it. So again, we put it like this, E. This goes here to the E double star. This is my J. And now I take functional. So let's put it like this. I put here functional. So this is functional that goes, I put here psi f. So this psi f is something that is acting on psi in such a way that this one is equal to psi applied on f, where f is a fixed element on the dual. So this goes R here. So now I need to take this composition and check if this composition is continuous. Is this continuous? Continuous. And with respect to this topology, is this continuous? So this one, of course, you can imagine that this is nothing else than this is psi f composed to J. So let's check what it is actually. So let's check, evaluate it and check what is this. This is J, and put here like that on X. So this is the same by the definition which is here. This is by the definition that is here. This will be the same as J of X applied on F. But that one is nothing else than F applied on X. So you can see, wow, that's nothing else than this is F. And of course, F belongs to the E star. So this generates this topology. This generates this topology, those maps. So that's definitely continuous. So yes, we can say it is continuous. Check mark. So now the conclusion of the proof is just a simple remark, conclusion. To conclude the proof, we notice that the continuous image with respect to this topologies, to appropriate weak topologies of a compact set. So in this case, B, weakly compact, because this is a weak topology, is compact. So we get that J of B is compact in this topology, E double star E star. So if it is compact, it is closed. It is closed. If this is closed, thus the J of B is equal to the closure, to its closure. With respect to this topology, so put it like this, E double star E star. But this closure by the lemma number 2, lemma Gonstein, lemma number 2. So this closure is nothing else than the ball of that one. And what did we get? That this ball is equal to that ball. And then, of course, since I can write it down, E is equal to union, and I have here n is equal 1 to infinity, and I put here nb, and that's the same thing as a union n is equal to infinity, and this will be nb double star. I'm getting this is E star. So the space is reflexive, and we are done.